It's the most wonderful time of the year. Or at least it seems that way, because last year at about this time we were doing a bunch of battery research technology updates from some exciting research papers. And this month we've got another quadriptych of excitement. I'd give you more of an intro, but I think the bell's about to ring, so if you could all open your textbooks to chapter 6.02214 times 10 to the minus 23, we'll make a start. We've got a lot to get through today, class, so first, I'd like you to jot this down in your copybooks. Okay, class, okay. Settle down. Settle down. Okay. Good. Jones, do not put that bubble gum in Sarah's hair. Right. So, we have got 4 papers to go through today. They're all linked in the down below, and before I begin, I want to say a huge thank you to the authors of the gel electrolyte paper for kindly sharing a copy with us. Since we are very small and don't have institutional access to journals, we are kind of reliant on the kindness of strangers to get these papers. And also to the kind viewer who helped us when another of the paper's authors did not reply quickly enough for this video. You know who you are. Thank you very much. And I should also remind you that you'll find more in-depth notes than YouTube allows on our website at www.transportevolved.com, where you'll also see some links that I've put in to cover basics if you're wanting a little refresher on how batteries work. We're going to start today with a paper that interestingly links to one of the papers we covered last year. That was high energy, high power sodium ion batteries from a layered organic cathode. Link on our website. And today's first paper, which is Nanostructured Sodium Vanadate Hydrate as a versatile sodium ion cathode material for use in organic media and for aqueous desalination by Commanderou, Stolojan et al. Well, that has some pretty close links. Now, the last bit of that, the desalination, isn't related, although it is interesting. But the former part of the problem that they're trying to solve, that is improving the structure of sodium ion cathodes in sodium ion batteries, is a materials problem that both of these papers were examining, and while the means are very different, the end goal is very similar. For those unsure, aqueous desalination is a chemist's way of saying we used fluid to flush away the salt, by the way, because we're not going to talk a great deal about that section. That end goal, making it easier for the sodium ions to move through materials, that is something that has been worked on for a long time. If you take a look at your periodic table, you'll notice that sodium sits just below lithium. And if you remember your periodic table from school, you'll remember that means sodium atoms are larger than lithium. That's because sodium has 11 protons and 3 electron shells, whereas lithium is a svelte and slippery little thing with just 3 protons and 2 electron shells. And the problem with sodium being bigger than lithium is that when you need to shove a sodium ion through a material as part of the process of charging and discharging a battery, you need a really big space in the material for it to pass through. Otherwise, the material that you're passing it through gets damaged. So both of these papers are looking at making nice wide pathways for the sodium ions so they can slip through a little more easily. You know, like attaching a freshly filled tool to a nipple and squeezing firmly and applying some smooth, clean...
Are you wanting us to be added to another list?
What? I don't know what you mean. I was just talking about applying some fresh grease to the nipple on a trunnion just to make sure that my car's suspension doesn't seize up.
Hey, we are already on 4 lists, Kate. 4. And you shouldn't even be on the fluffy one because, well, no more lists.
Well, about that, I mean, there is something appealing about Actually, you know what? Never mind. We should get back to the video. In the case of the paper we looked at last year, that was done by using a large organic molecule, Bis-tetraaminobenzoquinone. Basically, 2 hexagonal carbon rings, that's the benz bit, joined in the middle with a couple of nitrogens and some nitrogen, hydrogen, oxygen bits hanging off the rings. It's emerged as a really rather interesting material for use in batteries with high specific capacities and excellent conductivity. We did a whole video about it last year, and yes, I really should go find my organic chemistry model kit for doing these videos, but it's up in the attic with my RISC PC. Okay, so bis-tetraaminobenzoquinone is held in place with hydrogen bonds to prop apart the layers and make it easier for sodium ions to diffuse through. It basically fills the same role you'll find cobalt used for in NMC batteries. That's been the default type of EV battery chemistry for the last 10 years. Cobalt stabilizes the electrode and makes it easier for lithium to glide through. In the case of the paper we're looking at today, this stabilizing and gap-making role is done by, well, and this sounds stupidly simple, but it's not. It's done by not drying out the cathode material as thoroughly as you normally would. Sodium vanadate has been used as a cathode material in sodium-ion batteries for a while. The reason the anhydrous form is used, that's sodium vanadate with the water sucked right out of it, is because water is broadly thought to be bad for battery longevity. The water molecules in batteries have, historically, been found to shorten lifespan, causing the battery to degrade through reactions with other substances in the cells. The H2O, or dihydrogen monoxide as I like to call it, can react with other substances and release hydrogen and oxygen. This can lead to the battery swelling and or the release of flammable vapors. And even tiny amounts of water can interrupt the formation of the interphase layer. That's the layer that forms on the first charge of a battery, which can impact its capacity and its service life. All in all, water in batteries has historically been considered a bad thing. But interestingly, Commanderoo et al. Found that by keeping a very specific amount of water in, through a process of taking the sodium vanadate hydrate and drying it for different lengths of time, the resulting cathode material had water acting as possibly molecular pillars, as well as being physically trapped because the specific tight grid structure referred to as a high aspect nanobelt. As any fashionista will tell you, you really can't go wrong with a good belt. The high aspect ratio nanobelt, with its grid structure, also holds the water in place. Along with that, the ionic bonds between the sodium ions that are between the layers and the oxygen atoms in the water create a hydrated ion complex that's just too big to move around. Altogether, it creates a much more stable integration of the water molecules into the molecular structure of the battery, preventing the water from interacting with things that we don't want it to. Basically, hopefully preventing all those side reactions that would typically cause cell degradation. One of the really interesting things about this research, which we're not going to get into here, is that it's also useful for desalination. Given that we seem to have opted for let's see how hot we can crank this baby up with our planet, finding sources for drinking water is going to be an increasingly pressing concern if our species is going to manage to stay on this unfashionable rock that we're making increasingly inhospitable. And a new and super effective technology to assist with desalinating seawater that's sadly going to be rather important. Now, this is really early in the research process. As it stands though, the authors tested the battery up to 150 cycles, with it maintaining stability, which doesn't sound like a lot, but it is vastly better than you would expect for a battery with water in it, and certainly promising for future research. And importantly, the battery provided a specific capacity of 280 milliamp hours per gram. Historically, we've seen up to around 220 as the peak. Additionally, the moist battery, if we can call it that, Well, wait, I'm told that we cannot in fact call it the moist battery. The wet battery? No, also that. Not good. Okay, the battery with water in it was able to charge faster than the anhydrous, that is the dry sodium vanadate based battery. So yeah, this is something to keep an eye on. Alrighty, time is short and we've got 3 more papers to get through. It's been a busy start to 2026 in battery research circles. At least in countries which are trying to move technology forwards. So next up is this little ditty: practical lithium-organic batteries enabled by an N-type conducting polymer. Now, batteries have mostly made extensive use of traditional organic materials like carbonyl compounds. I know we're getting a bit into the weeds here, but if you remember your school chemistry, oxygen atoms have 2 little leggies, and in carbonyl compounds, both the little legs of the oxygen atom are bonded to one carbon. Because the oxygen-carbon bond is polar, that is, the electrons like to hang out with the sexy oxygen atom, which makes it slightly negatively charged, and the carbon slightly positively charged. That whole polar charge thing makes the compound reactive. And yes, I'm simplifying. I can hear Mr. Sprouse, my not quite grammar school chemistry teacher, coming for me with another one of his terrible chemistry jokes now, so I'm gonna leave it there. These carbonyl compounds do the actual energy storage bit of being a battery. The traditional organic materials used have challenges. Typically they're not actually very conductive, and so what you have to do is throw in a shit ton of extra carbon to get them to work. Typically between 20 and 70% by weight. Now, why that is a problem is you've got this fancy organic material that's designed to provide energy storage, basically doing the battery bit of being a battery, but instead of using that, your material is mostly made up by the equivalent of the wiring to get to the actual battery. And what Lee et al. Have found is that polybenzodifuradione, or PBFD, okay, that doesn't work. Sorry. PBFDO, which is a highly conductive organic compound. Specifically, it's an N-type conducting polymer, a plastic that has a skeleton of benzodifurandiones. The specifics of that structure, it's straight. And you know, I don't normally do straight stuff, but I'm making a special exception here. And when I say that it's straight, it, unlike a Republican political convention, is actually straight, not just deeply ashamed. Also, importantly, PBFDO doesn't have a doesn't have a bunch of side chains, so it's also flat. Because of all this, the whole thing stacks really, really well. It also has alternating single and double bonds, allowing the electron orbits to overlap. Mean that PBFDO has a startlingly high conductivity for an organic compound. And when I say startlingly high, I really mean startlingly high. To give you an idea, conductivity, which is measured in Siemens per centimetre, is basically a measure of how easily a material allows electricity to flow. A measure where bigger is indeed better. If you're wanting a conductive material, when you look at conventional organic compounds, they typically measure in the 0.001 Siemens per centimetre to 0.000001. That's a decimal point with 8 zeros before you get to the number Siemens per centimetre. PBFDO, it exceeds 2,000 Siemens per centimetre. I should take a moment here to say that the reason it's comparatively so high is the completely different way it's functioning. You're not getting ions to migrate through a liquid like, you know, trying to swim lengths while the sorority party's drunk and on inflatables in the pool. Instead, the material itself is just actually conductive and the electrons are just running straight through it. It's a wire, not a swimming pool. Now, compared to, say, carbon nanotubes which can manage 1 million Siemens per centimetre, it may not seem that great. But the thing is, the PBFDO is not just doing the conducting bit of the job, it's also doing the battery bit of the job. You're not having to mix a ton of carbon in, which is just getting the energy to the place where it can be stored. PBFDO can both hold the lithium ions and get the electrons where they need to be. So what you need to actually be comparing it to is a complete conventional inorganic electrode. I fear I'm going to have to introduce another concept for you to get through this bit. That is the concept of mass loading. So mass loading is basically the amount of active electrode material. In a traditional organic compound battery, that would be the organic compound, not the pile of carbon you've mixed in to make it work, that's on a unit area of the electrode. It's a measure of weight per area. So milligrams per square centimetre is a reasonably common measurement. When you have a higher mass loading, you usually get a higher energy storage capacity. That's areal capacity, milliamp hours per square centimetres, for those wondering how that's measured. Lab studies have limitations that mean that they can't hit the kind of mass loading that you see in actual production batteries. Often physical restrictions limit them to below 3 milligrams per centimetre. For reference, actual production NMC 811 electrodes range from around 10 to 30 milligrams per centimetre. But even in the lab, the PBFDO cell managed 206 milligrams per centimetre. The PBFDO pouch cell they created managed to hit 255 watt-hours per kilo, which is comparable to current lithium-ion cells and, really importantly, remain stable and functional at minus 60 degrees centigrade, that's minus 70 Fahrenheit, and capacity actually increased at 80 degrees centigrade, or about 176 Fahrenheit. Anyway, beyond the bits I've mentioned, good energy density and working over a wide temperature range, it also apparently survived a nail penetration test without going whoosh, and is much more flexible, allowing for bending without stopping working. This is definitely not a feature of existing organic compounds and means that we could start to see more wearable electronics based on this technology. Okay, we'll do the last two papers in a minute, but first I'd like to let you know that we're here because of our amazing community of supporters on Patreon, YouTube, Discord, and Ko-fi. Unlike a lot of channels, we don't take big advertorial sponsorship deals, and we only exist because you support us. There's a link in the down below on how to join, plus links to our channel on the Fediverse, because in addition to being independent, we also think everyone should have free access to information. Right, next in our little literature review is this article from Joule. Gel electrolyte featuring a parasitic salt-phobic network enables anode-free lithium batteries with long cycle life and enhanced thermal stability. Far be it from me as a pretty much retired biochemist to comment on choice of title, but I really feel like they're removing any element of suspense here. I mean, they've really spoiled the whole paper. That is no way to get popular on BookTok. Okay, so we're into the world of a whole different problem set here, so steel yourself for me explaining a bunch more things very, very approximately. Lithium, as you might remember from school, is very, very soft. Soft like...
Du pain, du vin, du boursin.
Only... don't go spreading lithium on your baguette. That's some free healthcare advice. It's a really bad idea. So if you've ever smeared soft cheese on a thing, you'll know that it gets kinda all over the knife and you have to rub it off on the bread or lick it off the knife or whatever. And the same thing's true of the manufacturing equipment that's used to make lithium electrodes. The fact that lithium is so soft means it leaves residue and gets contaminated and contaminates equipment, and also the fact that it's incredibly reactive with air, water, anything really means that manufacturing processes tend to be quite complicated. Now, if you're in the US, you might have forgotten what a scientist actually is. They're the folks who test theories using research and science. Not the folks who, cancelled the funding for most of the research projects in the US because they'd quote unquote read something that turned out wasn't actually related to, the topic of the studies that they were cancelling, but they had seen that the study had the word black in the description, and they knew that black people shouldn't have money. Is it any wonder that the US is falling dramatically behind on research? On the plus side, I suppose Anish Kapoor is going to struggle to get a blacker paint. So one of the ways that scientists have dealt with this, or considered dealing with it, is to just get rid of the anode. Okay, so in your bog standard lithium battery, as has been used in laptops and all sorts of technology since just after my Acorn A4 left the factory with its nickel-cadmium batteries, you had a cathode and an anode, and the anode in a typical lithium battery is a thick layer of either graphite in which lithium ions wedge themselves, or an actual lithium anode. What folks are looking at creating right now is anode-free batteries. Removing that anode has the potential to make the battery much lighter, much cheaper, and more energy dense. A lithium-nickel-cobalt-aluminium cathode anode-free cell has been demonstrated to have 24% higher energy density than a lithium metal battery and 78% higher energy density than lithium-ion batteries. So you can see why this might be an appealing technological shift. However, current designs mostly require the lithium to coat a copper foil during charging, a process which often happens unevenly and which can sometimes result in the lithium bonding permanently and thus being lost to charging. So these cells tend to have a short cycle life. They also tend to require quite a lot of pressure to keep them functional. Oh, and a lot of the electrolytes that have been used have been flammable, which doesn't help with the whole avoiding things being flammable. So what they did in this paper is they created a new electrolyte. Typically in a liquid electrolyte, lithium ions are wrapped in solvent molecules. In this new electrolyte gel, which is salt-phobic, it pushes the salts into the middle of the dance floor at the party, and the solvent mostly gets sucked into the walls, where it quietly sips beer and attempts not to meet the eyes of any passing girls. This stops the solvent getting in the way of the lithium ions and acts as a sort of filter. The way they did this is with a small amount of fluoroacrylate. One of the ways that battery researchers have been working on this challenge previously is with fluorinated non-solvents. The solvent in the battery is the liquid the lithium salt dissolves in, and the fluorinated non-solvent is a substance that lithium can't dissolve in. Putting a bunch of non-solvent in means that the lithium is forced to hang out in the solvent in restricted places. The good thing about this is that the fluorine makes the liquids very resistant to fire, and it also helps with making the electrolyte thinner, which makes it flow better. However, fluorinated compounds are often what are called forever chemicals that don't break down and have high climate change associated dangers, and they can also have unpleasant health effects or be toxic if they leak during the manufacturing process, or if they do eventually react, which they do eventually in a fire, and are released. One of the things it used to be important to know is that you shouldn't touch burned out cars because the foam in the seats used to use fluorinated compounds during its manufacture, and it had the potential to leave hydrogen fluoride on the surface of the vehicle, a substance that can both dissolve skin and bone, and that is on its way to, well, once it's in there, it starts interfering with the way your body uses calcium and causes heart failure. These highly fluorinated compounds have the same risks and are also much more expensive than traditional solvents, and they also make recycling harder. Massively reducing the amount of them from the 60 to 80% that's typical for non-solvent additives to electrolytes to the 2.5% used in this cell is actually a huge advance. Okay, so these lithium ions are held very differently thanks to the gel's parasitic structure, and so when it charges the anions, which are closely bound to the lithium, they find themselves dumped neatly and smoothly on the copper surface, creating a nice, neat, solid electrolyte interphase layer without pokey little dendrites forming. Also, impressively, for a lab test cell of new technology, it managed to retain approximately 85% capacity after 150 cycles. It also took a drill through the cell, not only without catching fire, but also when the drill was removed, the cell regained some function, which is, pretty wild. And again, this is a paper that's fairly far from production ready, but it's potentially a significant leap forward in making cells lighter, cheaper, and safer. Alrighty then, we are into our last paper. This paper uses fluorine, in this case hydrofluorocarbons, as part of the electrolyte. Historically, most battery electrolytes have been based on oxygen or nitrogen compounds, which are great for dissolving the lithium salts, but they also stick really hard to the lithium, which means that the lithium ions need quite the shove to get them into the electrode. A problem that's particularly prevalent at very cold temperatures. In this paper, the researchers created a new solvent, 1,3-difluoropropane, a fluorine-based electrolyte which still allows the lithium to dissolve in it, but because it's less clingy than an incel finding their first girlfriend, the lithium ions can move much more freely and easily. This has the potential to massively increase the performance of the battery. Not only that, but they carefully nano-engineered the molecules to have a specific shape that prevents them from clumping together, so even at very low temperatures, the electrolyte remains properly liquid. When we talk about traditional lithium-ion batteries needing to be kept nice and cozy, mostly at temperatures that humans tolerate, that's in part because if they get too hot, they tend to catch fire, but also because if they get too cold, the electrolyte stops being liquid and the lithium ions stop being able to get anywhere useful. By creating molecules that basically don't stick together with each other, they made an electrolyte that works down to -70 Celsius to -94 Fahrenheit, which means that the batteries don't stop working when it's very cold. A really useful thing if you're someone who lives somewhere in bits of the world where it consistently gets really chilly. Previously, we've needed lots of complex battery heaters and such to keep lithium batteries from getting too cold, at which point they stop working, but this could change that. Also, because the lithium ions can move much more easily, there's the potential for there to be much faster charging, and the electrolyte also allows for higher voltages. While it does still work when it's cold, compared to its room temperature performance, it's not great. Remember how conventional electrolytes tend to live somewhere in the 0.0001 Siemens per centimetre range? Well, at room temperature, this is way better than that, with conductivity of 0.01 Siemens per centimetre. So conductivity-wise, this stuff is on fire when it's at room temperature. Not literally on fire, obviously. I just mean it's really conductive. But when it gets cold, down at -70, it's down to 0.00029 Siemens per centimetre. So when it's cold, it's no longer on fire. It's just pretty good. However, there are some downsides, some of them significant. It is probably rather expensive and somewhat more complex to produce than traditional electrolytes, and will require a well-sealed package because the last thing that we want is a ton of hydrofluorocarbons escaping into the atmosphere. It also may not work well with all modern electrodes, but those are all challenges that we can hopefully overcome. Honestly, this is all really exciting news for battery technology. Big advances that the rest of the world will be quick to take advantage of, and something to look forward to when we can get past having an orange idiot in charge of the US. Thanks for watching to the end. Let us know your thoughts on these new battery papers. Do you think exciting things are coming down the line, or is this just research that's years and years from any kind of commercial reality? Let me know your thoughts down below. We are 100% independent, and if you'd like to help us stay that way, there is a link in the down below to support us on Patreon from $1.50 a month. So you can join the long list of amazing channel supporters scrolling past right here. You can also send us money on Ko-fi and, of course, buy some swag from our swag store. And please hit subscribe. YouTube won't tell you reliably that we've pushed a new video, so make sure you also follow us on social media or join our Discord chat room. Thanks for watching. thanks for helping be the positive change in the world. And for one last time, do me a solid. Always, always keep evolving.